Hello and welcome to the next event in the South African Deep Learning IndabaX Roadshow. We're very excited today to introduce Daniel Godoy, who will be doing the PyTorch tutorial. But before we get to that, I'd just like to introduce the Deep Learning IndabaX. This is an endeavor that spun off the main Deep Learning Indaba, which aims to strengthen African machine learning. And we welcome all members of the community, and we're very excited to have you online with us today.
Thanks.
There are these IndabaX events all over the continent, and if you haven't had a look yet, please check out the website and you'll be able to see all the countries that are currently represented. So as I said, we're aiming to strengthen African machine learning, and while we can't meet in person at the moment, we're really excited to have you joining us online. So this is your first time on Crowdcast, welcome. And just so you know that in the bottom left-hand corner of your screen, there's an audio help button. So if you're struggling with your connection, it's a bit slow, or you're struggling to connect, please don't leave. There is a compatibility mode that you can find there. So we'd love to have you join us live and throughout the entire event. And then just a special shout out to the organizing team that has made this possible. It's been a lot of hard work behind the scenes, and but we're more than happy to do it, to have everyone learning along with us. If you haven't seen the IndabaX website yet, have a look. We have amazing events lined up right up until the end of November, so sign up today. And if you haven't joined the Discord yet, please do. It is the link is the big green button, join the community button just below the Crowdcast screen, and from there you'll be able to join the Discord chat and meet all your peers and possible colleagues. And there are some amazing competitions happening as well, and these can also be found on the website. I'll paste all these links in the chat. And special mention to all our sponsors. We are very happy and grateful for the assistance, and this just goes a long way in making these events possible. And so with that, I will hand over to Daniel Godoy. I will paste the link to his book, but he is the author of the step-by-step deep learning guide with PyTorch, and I'm very excited to have him join us today to step us through this tutorial.
Thank you very much. Thanks. Let me share my screen and then we can start. Okay, so yeah, I hope everyone is seeing my screen already. Thanks for having me here. It's my pleasure to introduce you to this workshop, which is targets beginners. This workshop is based on the first part of my book, which is about building models using PyTorch in a very step-by-step way. So I really take my time to explain the concept, and this is what we're trying to do here today. So you have received the link to the GitHub repo for this workshop, right? So this is the one that was posted in the chat. What you can do if you want to follow along, you can open it in Google Colab, right? Because this is the easiest way of going through the materials. You can also install it locally if you want. There are instructions in the README, but it's much easier if you just go with Colab, because it's a very light notebook, so should have no problems running it. One thing that I don't know if everyone is familiar with Google Colab, but one thing that's important, once you open it, you can check here the runtime. You see if you have like a GPU or a TPU or none. In our case, we're keeping the GPU because it will speed up a little bit the models that we have here when we're not doing any heavy models or anything that's very demanding, but it's nice to be able to work with the GPU from the start. Right, so also if you're not familiar with Colab, at first it's gonna warn you, okay, yeah, someone else authored this notebook. In that case, that was me. But yeah, you can trust that I didn't do anything weird with that, so we can just run. This first part is just for display. This will make a difference if you're running it locally. For Colab, it won't actually change anything. So just a brief introduction about myself. I'm Brazilian. I'm currently living in Berlin, in Germany. and I moved here 6 years ago to attend a boot camp here in Berlin called Data Science Retreat. I was a student there, and then I became a teacher. I started teaching first Apache Spark, then the basics of machine learning, and then at some point I started writing blog posts. People liked what I wrote, and that's got me started with my book, which gave rise to all of this workshop included. So why PyTorch, right? So why are we focusing here on PyTorch? First, this is the fastest growing deep learning framework, right? It's used by many different companies, also from some very popular courses like this Fast AI Deep Learning for Coders. I really like this quote for Andre Karpathy. He said that, yeah, I'm using PyTorch, and that he has more energy, his skin is clearer. Of course, this is a funny joke, right? But I think it's fun, right? If you can have fun while coding or while developing something, I mean, that really helps. And at least for me, and I hope that for you, as you get more familiar with PyTorch, that you're also gonna feel like that. That's really that's a delight to develop models in PyTorch. Then, what's the approach that I'm taking here, right? So in many cases, you see tutorials and documentation that they start already, yeah, you can train a model. So here it is, a computer vision based model based on trying to develop a really complex model for that. But this is not, I don't think that's a proper way of learning something that you're not familiar with, right? Because the model is complex, there will be lots of moving parts. So let's stick with the basics, right? Let's start with the most simple model that we can, and then we can focus on how PyTorch works. What are the different parts that compose a model? How we can train a model? It doesn't matter if the model is simple, right? Because if you know how to do it with a very simple model, you just have to replace it for a bigger one later on, and all the logic is going to still be the same. So we're starting with the linear regression because it doesn't get any more simple than that, right? Then I'm going to talk about a little bit of tensors. We're going to quickly visit gradient descent, talk about autograd, the dynamic computation graph, and then we're going to go through the different parts of PyTorch that you need to use to train a model, like an optimizer, a loss model, data set, data loader, how to evaluate a model, in saving and loading models. I also have some bonus material in the end that's not in the agenda because usually we don't have enough time to cover that, but it's also there if you want to pursue more knowledge on your own later. So having said that, we're starting with the linear regression, right? What's the simplest linear regression that you can do? A single feature X and one bias, right? So it doesn't get any more simpler than that. And then if you want to think of it as a neural network, you can think that, okay, this is a very, very simple neural network with one neuron that has one input, one output, and the called linear activation function. That means it just gives the output right away without any changes to it. So this is what we're doing. And to make it things even more simple, we're generating our own data. We're using a synthetic data set. Then why we're doing this? Because it's easier to know if you're going in the right direction if you know what your end goal is, right? If you have some data that you don't know how it was generated, you don't know for real what's the truth, what are the parameters that are driving that data. In our case, we're going to use a bias of 1 and a weight of 2. So we know the true values of these two variables here, right? 1 and 2. And this is what we want to learn, want our model to learn in the end. But since we know that beforehand, we know if it's going the right direction or not. So let's generate ourselves some data, right? So you see that this is just using regular NumPy. This is important for ensuring reproducibility. So if you are following along and you run these, you're going to get exactly the same outputs as I do. and this is important. And of course, we have to, after we have some data, the first thing that we do is the split into training and validation sets. We're not doing a test set here because this is synthetic, right? We're just trying to experiment with things. So I'm keeping it simple. If we split it in two, we can also visualize it. And these are the data. These are the data points that we have. You can clearly see that this is a very nice plot, right? Clearly there is a linear relationship between our X feature and our Y target. And of course, both training and validation, they come from the same data generation process. So we have very similar, the look is very similar between the two of them. One thing that I want to keep in mind, that we're gonna get back to this later, so keep this thought on your minds. The validation data is more well behaved, let's put it like that, than the training data, right? You see there is less noise. It's a tighter line across the points than the training set. So in a way, that's easier than the training set. Cool. Let's keep that on the back of our minds. And now let's start with PyTorch itself. So here I'm installing this Torch Viz, which is a visualization package. We're going to see this when you get to the computation graphs. But for now, I'm just importing the libraries. So where does everything start? With the tensor. Then we need to get the elephant out of the room, right? What is a tensor? And I really like this picture to illustrate the different kinds of tensors. So, but let's take step by step. So you know that if you're familiar with NumPy, you see that you can create a NumPy array. And the NumPy array may have as many dimensions as you want. You may have 1 dimension, 2 dimensions, 3 dimensions, right? Or 4 or 5, doesn't matter. So how does this translate into tensors? In a way, the tensor is going to be any array that has 1 or more dimensions. So basically, if you have 0 dimensions, that's just a single number, like, I don't know, 3, 4, whatever, just a number. And this is represented by this puppy, right? Because it's just one single element. If you have 1 dimension, we usually call this a vector. So you have like a list of elements. Then if you have a matrix, that's a table, right? Or a spreadsheet, you have two dimensions. And the moment that you go into 3 dimensions or more, these are technically speaking tensors. But for the sake of simplicity, it's very commonplace to just say, okay, 0 dimensions is a scalar. This guy is going to be a tensor. This dog is going to be a tensor too. And obviously, this is always a tensor. So we are calling vectors and matrices tensors for the sake of simplicity. So basically, almost everything that we have to work with are tensors except for the scalars. We can create all of these tensors the same way that we create a NumPy array. So if you are familiar with the np.array to create an array, you can do the same with the tensors, right? So if you run that, you see here it is. We have a scalar, a vector, a matrix, and a tensor in the end. If you want to expect what's the size, right, you can use size or shape. Like in NumPy, you also have the shape. So you see in that case, this tensor here is 2 by 3 by 4 dimensions. You can reshape them like this, right? So this is also similar to what we do in NumPy with the reshape. Just be aware that if you're reshaping or viewing, you're getting like not a real copy of the underlying data. Basically, you have 2 variables that point to the same area of data in the memory. So if I change tensor 2, I'm going to be changing the underlying data of tensor 1 as well. So be aware of that, because maybe you'll think, okay, yeah, reshape, now I have a different variable. And then if you start changing stuff, it may bring up different results that you expect, because you're actually changing more than one variable at once. So this is very important to keep in mind. If you want to really duplicate the values in memory, you can use different things like this new tensor or clone, right? So actually, you see here that Google Colab is complaining, yeah, you're using a GPU, but you're not using it for you. But we're getting there. So now you have tensors. Tensors are going to contain both the data points that you have from your data set, like in our case, but also the parameters. And then you're going to see how these two are different. But first, how do you actually convert the NumPy arrays to PyTorch tensors? And then you can use this very handy function that's called very appropriately stensor. And then if you do that, now both my X-train and Y-train NumPy arrays, they became PyTorch tensors. And then comes the GPU part that Google Colab just complained about. In this case, these tensors here, they are going to be like regular tensors. They live in the memory of the main computer. They are called CPU tensors. What if you want to use a graphics card, a GPU, and send these data, these tensors, to the memory of the card? You can use this method here called to, and then you send the data to a particular device. Then what is the device, right? Because, CPU, it's called here like CPU, right? But if you want to send it to a GPU, you can call it to CUDA. CUDA is this framework developed by NVIDIA that you can use to actually leverage the power of a GPU that was developed mostly for gaming to train deep learning models. What's interesting is that PyTorch gives us this method here, telling if a given machine, a computer, or has a GPU available for it or not. In that case, it's very, very best practice to just have this at the beginning of the code. Because then what happens here? If you have a GPU available, you want to use it, right? Because this makes everything faster. But let's say that you develop your model, you have like a notebook you want to send to a colleague of yours, and I don't know, maybe he does not have access to Google Colab at that moment. He wants to run on a local computer, and the computer does not have a GPU. Then if you have these, basically you get your bases covered, right? If it's available, you use it, GPU, great. If not, you just fall back to the CPU. And there is absolutely no harm in sending to a device, which is the CPU. If you send it to a device and the tensor is already there, it just doesn't do anything, right? So there is no cost in this operation. So basically what you're going to see here in this code is that first you check the device, and then you send your data directly to it, right? So this will probably take a little bit, because like now Colab is like initializing the GPU in the bag. But you still cannot tell the difference here, right? If you do type, you see this tensor here looks exactly this one. But now this guy here is living on the GPU. So how can you do that? You can use this, instead of using the regular Python type, you can use the type method of the tensor itself. And then you see now you have CUDA here, meaning, okay, now you have a live tensor inside the memory of the GPU, of the graphics card. And you can also bring it back, right? Actually, here I spoiled it, right? Because if you use NumPy to bring it back, it's going to complain. It says, okay, cannot convert a CUDA device tensor to NumPy. Because to bring, NumPy doesn't handle GPUs, right? Then what happens is you need to bring your tensor back out of the GPU, back into the main computer memory to become a CPU tensor. Then you can transform back into a NumPy. So this is what this message is all about. So you're going to see, then if I do that, now I have first CPU and then NumPy. And then this is, again, if you want to make sure that you want to bring it back to NumPy, you can always prefix it with the CPU method, because then you're safely making this transition without running the risk of getting this type error here. And then we have data points in tensors that we move to the GPU. Great. What's next? We need to make sure that our parameters are also GPU-based tensors. And the difference between a tensor that's for data and a tensor that it's the parameter B or W that we're trying to learn is that a tensor for a learnable parameter requires a gradient. So this is very important. This is the whole purpose of this parameter here. The moment that I say that a given tensor requires gradient equals true, it means that, okay, PyTorch is going to use this to compute the derivatives. We're going to see the autograd, which is computing the gradients. And this is going to be something that will be learned. You're going to be updated as the training process goes on and on. And the second point here, and it's very important, the moment that you create a tensor that's supposed to be a parameter, please make this device equals the device that you're using. Because I'm not showing this here in the interest of time, because this would be a lot of different information also. But if you don't do that and you want to use two to move to a different device, you may run into problems. So every time you create tensors for parameters, make sure that you're using the device right away. So if we do that, and if you're following along, you're going to see that now you have two different tensors with the devices here, right? And both requires gradient equals true, meaning these will be the parameters. So we covered a little bit of ground, basically with a short introduction to PyTorch and tensors and devices. And before going to the next topic, which will be gradient descent, I'm gonna see if you have any questions. Let me check. Okay, one question here: PyTorch versus TensorFlow. When is PyTorch a better choice? So this is tricky, right? Because I'm a fan of PyTorch. Basically, what happened, especially a couple of years ago, is that PyTorch was more geared towards research, because you have a lot of flexibility with PyTorch, and you did not have so many tools to deploy in production. So the deployment to production in TensorFlow was more mature 2 years ago. So most companies were still using TensorFlow because of this, mostly. But as time goes by, I mean, more and more people in academia working with PyTorch, is expected that this will be translated into some the need in the business also have these models deployed, right? So at this moment, there is not such a much difference. I mean, I think TensorFlow, especially for mobile in devices, for mobile devices, it's a bit more mature, but there is not so much of a gap. So now it mostly boils down to preferences, I think. I have more fun with PyTorch, but again, I was used to the TensorFlow 1 point something, which was not so great. And TensorFlow 2 is closer to PyTorch. Basically, they are converging. So I hope I answered the question. It's mostly a matter of preference these days. Okay, yeah, so the second question is, what are the main differences between PyTorch and TensorFlow at computation graph level, besides one static and the other dynamic? Actually, this was a difference that was important also a couple of years ago, but now you have the different modes for both of them, right? So you can actually work both ways with both of the frameworks. So this is not usually not an issue anymore. It again boils down to a preference. Okay, let me see if I have anything else. Okay.
No, I think that's it for now.
Okay.
Yeah.
Okay,
thank
thanks.
you so much.
Okay, let's move along. So let's talk about gradient descent. Gradient descent is an optimization algorithm, right? Its purpose is to minimize the loss. It's to find a better model that explains the data that you have. And the way that it does is by assessing how good or how bad your model is using the loss. So if you minimize the loss, you're getting a better model. We're going to see this in more detail. There are many different steps of gradient descent, right? One is called step 0, which is like just randomly initializing parameters. And then you have the 5 steps themselves, which is computing predictions, computing the loss, meaning assessing how good your model is, computing gradients, parameters, updating parameters, and then going back to the start. Why am I doing this? Why am I telling you about gradient descent? Because the training loop that you develop in PyTorch, it's always going to be mostly the same training loop. It goes through all these steps. Because in a way, what PyTorch is doing is just optimizing the model so it fits better the data. So it has to go through all these steps to actually train a model. And this is what we're going to see here. I'm taking one step back and going to NumPy for now, but just we're going back to PyTorch soon, so don't worry. First step, initialization of parameters. I know I have B and W, my 2 parameters, and then I have to start at some point. So here I'm just randomly guessing, right? B is 0.49 and W is minus 0.13. These are really bad because we know that this should be 1 and this should be 2. And ideally, after training the model, you're going to get these 2 parameters to match closely what the real ones are. The first thing that we do is computing the model's predictions. This is what's called the forward pass. It doesn't matter if your model is very simple like ours or a very complex neural network. You're going to give the inputs, you're going to get the outputs. That's the forward pass. These are going to be predictions. Of course, since we are randomly initializing the parameters, it's expected that the predictions are going to be awful, right? They're going to be really, really bad. Because, come on, this is a random model. It doesn't know anything. We know that they have predictions, and they know that they are bad because they are random. But how bad they are? So that's the role of the loss. The loss is going to tell you how bad your model is. And here I would like to highlight the subtle but still fundamental difference between error and loss. The error is the difference between actual and predicted computed for one data point. So you have your first data point, and you predicted this, but your real value was that. That was the error. But of course, you cannot have one error of one data point is not enough to tell you if the model is bad or not. Maybe some data points are going to have higher errors. The others are going to be lower errors. We don't know. How can we tell if the model is an aggregation is good or bad? We have to aggregate the errors some way. For linear regression, we know that the proper aggregation for it is the mean squared error. And I always forget to fix this typo here. So mean squared error, sorry. Which is basically the difference, the error that we computed here, we square and average them out, right? So that should be fairly simple. But there is one thing that that's important to take note when you do this aggregation. You can do this aggregation either using all your data points, and if you're doing that, you're going to be doing what's called batch gradient descent because you're using everything. You can use one single data point at a time, which I said, okay, only one seems little, right? If you do that, you're going to be called the stochastic gradient descent. And if you do anything else that's not only one, but it's also not all of them, that's called mini batch gradient descent. And this picture here illustrates very well. If you use everything, you're going to get this nice path, right? So this is the point where the loss is the minimum. This is what you're trying to get to. If you use a batch gradient descent, it's going to take its time. It's going to slowly converge there. If you use only one data point at a time, it's going to be called the stochastic. And this, you see it's all over the place, right? It's moving everywhere, and it's getting close to the red dot, but it's never settling on it. Because if you only look at one point, you cannot do much, right? You walk all your way towards there, but you're never going to settle on anything. And then, of course, mini batch is something in between. It's faster than batch, but more stable than stochastic. So you're going to wiggle around, but you'll eventually get there. So it's a good compromise between stability and speed. And this is why everyone uses mini batch gradient descent most of the time. So for now, let's use batch gradient descent because we have only a handful of data points and our problem is quite simple, right? So you're using all of them for now. So if I compute errors, this is gonna compute errors for every data point. This is gonna make the squares and the average, and my loss is 2.74, which is a high loss for this problem. What do we do with that now? So that was step number 2, right? We computed the loss that tells our model is really bad. Now we're going to use this information, this loss, to compute the gradients. What is the gradient, right? Gradient is a partial derivative with respect to of the loss with respect to a single parameter. So we're going to compute the gradients for the 2 parameters that we have, b and w. And basically what the derivative is telling us is how much the quantity that we're computing the derivative for, the loss, changes if one of the parameters changes by a little bit, right? So basically, this summarizing an informal way of gradient is how much the loss changes if one parameter changes a little bit. I have the formulas here for the sake of completion, right? So if you do compute the derivative of mean squared error with respect to b and w, you're going to get these expressions, which are translated in code here. If we get that, we know that if we increase b by a little amount, our loss is going to decrease 3 times as much. And if we do that for w, it's going to decrease by almost two times as much. I don't know about you, but I'm not a fan of computing this manually. So this is actually the most important part of PyTorch, is going to get rid of this part for us. It's going to compute all the gradients, all the derivatives, everything is going to be computed automatically by PyTorch itself. So you don't have to worry about this ever again. But still, let's see if we can, if we know how this works from first principles, we should be able to replicate it using PyTorch. So if we know that, now we have these measures, right? These gradients, they're going to tell us how we should change our parameters to make the loss smaller. In that sense, what we have to do next is actually make our parameters better. And what we're doing here is updating the parameters using the gradients. So these gradients here, they're going to be used to update the parameters. So you see the parameter is the same as it was, minus a factor here multiplying the gradient. This factor, this eta, which looks like a the letter n, is the learning rate. The learning rate is the most important parameter of all. Sorry, just a second. The learning rate is the most important hyperparameter of all. It's going to tell you how much you want to use, how fast you want to your model try to learn the parameters. If you go overboard, you're going to run into problems. If you get too small, you're going to takes a lot of time, and then we're going to see how this has an impact on the model training. For now, we're using this 0.1, which is high if you consider bigger models, but for a simple model like this, it's still fine. So if you replicate this formula into code, you're going to have this, and now the values of the parameters are 0.8 and 0.045. So it got better, right? Because we know that this should be 1 and this should be 2. So they are moving in the right direction. And we just executed one step of updating parameters. If we do this over and over again, we'll eventually get there. But before we go to the looping, I wanted to show you the impact of the learning rate, which I think this is very important, so that you have this clear in your mind, and that you have a good understanding of the impact, because this is going to make a world of difference when you're training models. This graph here shows very well the different impacts. If you have a learning rate that's too high, very high, you're going to have increasing losses, meaning your model is getting worse as you train it. Of course, you want to avoid that, and that should be fairly easy to spot, right? If the loss is increasing, oh, something is wrong. If you are too conservative and you want to make it very, very low, it's going to decrease very slowly. It'll eventually going to get you there. If you had all the time in the world and all the budget in the world, because if you're using GPUs unless if it's like a free one like Cola, but if you're using cloud computing, you really have to pay for it. If it takes too long, this means it's going to be expensive. And usually you also don't want that. If it's high, but not that high that's so bad that goes up, you may have a false impression that, oh, this is going really well, but then it gets stuck, right? And ideally would like something that goes fast, but not as that fast, but it goes steadily down and eventually going to get you there in a good place. This is really tricky, right? You cannot know beforehand what's the perfect or the best learning rate for something. For an example like this, you may even try easier to find, but for a bigger model, a larger model, this will not be the case. This is also some sort of an art. You have other methods you're not going to see here now, but I want you to really have this in mind, that the learning rate is the most important part. I developed this. I can show you how it works. Then you can also use it later to visualize and to interact with this in an interactive way. Sorry. So let me show you how this works. Okay, and you see it's trending. Okay, there we go. So we have a start. So this is where it's going to start. See minus 1.5 here. We have a convex function, meaning it's a bowl shaped. It's really pretty and nice. You have a learning rate that you can change here, and you have the number of updates that you want to use. So, I mean, this is not fully interactive because you have to run this when you change to have an effect on this one. But you see, this is the starting point, and then after one step, it's going to get to the red one. And then if you switch to the next, it's going to next point, and so on and so forth. And you see that after 10 steps, it got almost there, but not quite. Then your first thought, okay, what if I use a higher learning rate of 0.3? Right, and then if I do that, I have to run this guy again, and you see that now it take one step is already really close to it, and then if you do a bunch of steps, 4 or 5 steps, it's already there. So you see that a higher learning rate got you faster. What happens if you got really carried away and you go with, I don't know, 0.9, which is like super high for this? See, now you're not going the nice path, going down the hill. You're jumping to the other side, and then you're like ping pong going back and forth, right? So you're still gonna get there. But of course, if you have something that's really bad, like 1.1 in this case here, actually, this is an example. The loss is getting worse, right? So you're getting from this point where the loss is 2 to 3 point something, and if you let this run, it will go off the charts, literally off the charts. And this is for a very nice bowl-shaped loss, right? If you have something that's called no convex, right? So in the case that's just a different shape, see here all the bets are off, right? You can have something that goes like this, and yeah, okay, nice. But if you have a higher learning rate, then you see that, oh, you're going there, and then you're going somewhere else. You see it's all over the place. If it's even higher than that, then yeah, you're going to the other part. So yeah, basically the purpose of this is to give you a tool that's very simple. Still, it allows you to experiment with only two for now, right? A very well-behaved and something that's a little bit not well-behaved, like the bowl, and you can see the different impacts. Now imagine this is just 2 dimensional, right? Actually 1 dimension. You have one feature here. I only using W, and you get a loss. If you have a real model, you cannot visualize it because it's like a multi-dimensional space. And it's going to be even more complex. That's why the learning rate is a tricky parameter to set, and it has a very important impact on how the model trains. Because in a way, training means, in that case, getting here, or if you're not so lucky, you may get here, which is not as a second best, right? So basically, this is what gradient descent is, this sequence of steps. We have done this with NumPy, and this will be done over and over again. So every time that you use all the points in your data set at least once for updating, you're going to be doing what's called an epoch. An epoch is complete whenever every data point has been already used once for computing the loss. In our case, one update is one epoch. Why? Because we are using all the points. So that's trivial, right? If you use all the points to compute the loss, compute gradients, update parameters, there you go, one update, it's one epoch. Second time going to be the second epoch. If you have stochastic or mini batch, there is decoupling between one update and one epoch. You may have many updates inside of the same epoch, and we're also going to get to that. Now we're still using one, and we have all the steps lined up here, right? Epochs 1000, that's a lot, but that's a very simple model. We start randomly, that was step 0, and then you compute the forward pass, the error, the loss, the gradients, and then you update. And if you do this, there you go. We have B almost equals 1 and W almost equals 2. We know that these were the two parameters that we had, right? Meaning that this loop here, using NumPy only, is perfectly capable of computing the derivatives and implementing gradient descent to minimize the loss and get the best possible parameters for this model. Now, what we're going to do is, basically, we're going to use this structure, this loop here with all these steps, and we're going to torch it, each one of them. Because these are ways that we're doing all this manually, right? Using NumPy to compute manually prediction here, and manually the error, and manually the gradients. And PyTorch is going to make all of this easier. And that's why we're going to start replacing them one by one. Just to make sure that we are like having a sanity check, we can use scikit-learn to compute this, and you see that we got same results. So, okay, we have a working model. Before we go to the PyTorch, let me check. I have a question here. Is PyTorch suitable for both research and for production level models? Yes, at the moment, yes. If you have many, PyTorch added many tools to its portfolio to the framework. So now we can have decent deployments using PyTorch. You have all sorts of optimizations to make the model smaller, so you can prune the models. There are different ways of parallelizing them in production as well. So at this moment, PyTorch is safely a mature framework for production deployment as well. Okay, so getting back to our workshop, the next, or as I mentioned, the part that's the most complex, or the part that would be harder to implement manually, is for sure the gradient computation, right? This, because mean squared error, the model, all this is fairly trivial. But if you get a more complex model, this is going to get out of hand really fast, because you have many parameters you're going to have to compute for each one of those. So let's see how PyTorch can handle that. We're not doing this manually anymore. We're going to take advantage of using PyTorch backward method. Backward method is going to basically take one tensor, in this case for the loss, and use it as a starting point for computing gradients for all the parameters that are involved in the computation. So let me illustrate this. Since we are going to a PyTorch loop, now we need to recreate the parameters as we did with NumPy. And you see, again, requires gradient true here, send it to the device. So we're going to have initial parameters. We can actually check the values, right? So 0.19 and 0.13. We're still keeping the manual computation of the forward pass and the error and the loss, but we're replacing step 3 now. Step 3 was this manual computation. Now we don't need it anymore. So if we do that, then you think, okay, where are the gradients now, right? because we just say loss backward. So what we do now? If you want to inspect the gradients, you can use each one of the tensors that represents a parameter, in this case, B or W. They're going to have a grad attribute. And then you see here, minus 3.3, minus 1.9. These are close to the one that we got in NumPy, but because our initial parameters are different, so they will be slightly different. What happens if you run this once again, and you check here? Now you have twice as much. So this is something that's if you're starting with PyTorch, this may trip you over if you bump into this and you're not aware of it. What's happening is that the gradients are always accumulated. What PyTorch does is it's if you run backward once, it's going to compute it, and if you run backward again, it's going to accumulate them here. So now you have twice as much, and you don't want that at this moment. You want to have the gradients for that run, right? For that epoch that you're running for training your model. So what you can do is you get the gradient, you can use the zero with the underscore to actually get rid of them. So you compute them once, you use them to update parameters, and then you can zero them to you can set fresh in the next iteration of the loop. At this moment, it's interesting to highlight that all the methods that finish with an underscore, they make a change in place. So you don't have to assign to a variable again. It will modify the underlying value of the variable that the method is being applied to. So in that case, zero underscore is going to zero this attribute of B. You may be thinking, okay, why is the default what's the default behavior to accumulate gradients? For a simple model like this, you don't need that. That's why we're zeroing it. But if your model is like really large, and then you may have problems with submitting, making a forward pass or computing gradients for many data points, because your GPU, like mine GPU, is only 6 gigabytes of RAM, so it's not very powerful. So you may divide a mini batch into even smaller batches and accumulate the gradients to mimic what a mini batch would be. But don't worry about that. Just to illustrate why this somewhat counterintuitive thing is here, but there is a reasoning for it. It's to allow you to train larger models in even if you have hardware constraints, right? So now we can replace the gradient computation with a simple call to the backward method, which is already making everything much easier, right? What's next? You have to use the gradients to actually update the models, to update the parameters, sorry. And this would be step 4. What's happening here? Well, here we have the full loop. I'm replicating it every time. So we have the full picture, creating the parameters, the forward pass, losses. Now here computes the gradients. We can see the gradients here. And then we're using the gradients to update both parameters using the learning rate and zeroing them in the end. And then you have this thing here, right? This is what I'm going to be talking next. If we run this, we see we got the proper results for the gradients, and we zero them in the end. Did the update work? Yes. Let's see what no grad is all about. Why do you need to use no grad to update the parameters? Because if you don't do that, I mean, you can. I'm not doing this now because it will be a diversion, right? But if you do that, you're going to start running into problems, because this operation itself is going to be interpreted as from PyTorch as something that. Sorry, let me take one step back. Everything, every operation is tracked by PyTorch. So how can you compute the gradients? To compute the gradients, it needs to keep track of everything that's happening. The moment that you're updating a parameter, you are just updating a parameter. This is not part of the regular operations, right? It's not part of your model. This is a part of the training. So you don't want this to be interpreted by PyTorch. Yeah, I need to keep track of that. You just want to make an update. So this no grad allows you to tell PyTorch, okay, yeah, please back off. We're just updating parameters here, nothing to do with gradient computation now. And this is what this context manager is doing. So it's gonna protect this operation from being interpreted in a bad way from PyTorch itself. We're gonna see what the dynamic computation graph is in a short while, so this will be more clear. If we have the full loop now, we see that we have gradients here and updates here and zeroing, right? So we have all the steps. 3 and 4 are already torched. So if you run this, we should get similar results, right? 1.02, 1.96. So we know that it's still with the proper, fully working loop. We have talked about the parameters and the grades, but we have not mentioned the loss anymore, right? How can we check the loss? You see that the loss in that case is really close to 0. It's still a tensor that lives in the GPU. You see here the CUDA. What if you want to make it a NumPy array? Remember that you have to do CPU, right? But here, okay, wait, why is the CPU not working? I have a tensor that's in the GPU. I'm sending it to the CPU, calling it NumPy, but still failing, right? So what's happening? There is one extra catch here, is the loss is computing gradients. The other tensor that we were doing before with the CPU and NumPy, they were just data, right? So they did not have gradients. The requires gradient was not true for them. But if you have a tensor that is computing gradients, it's attached to this graph. And then you have to detach it first. Here again, you'll likely not need to do this all the time, right? Because this is like very verbose and somewhat annoying, I must say. But it's important to know that if you get this sort of error, you see what's happening. It clearly helps you here, right? Oh, use detach first. Take it off of the computation graph so it doesn't mess with anything else, and then you can make a NumPy. Luckily for us, we don't have to do this all the time. You can use like item or toList, which are going to have all these steps in running under the hood, and then you still get like a regular value out of it, right? So this was basically a short introduction to AutoGrad and how PyTorch uses this sequence of operations that are performed in the code to keep track what depends on what, so it can tell you what the gradients are without having to compute any derivatives yourself. And we talked somewhat about the computation graph, but without actually explicitly showing what it is, right? And this is what I want to show you now. Let's say that we have some really simple operations like the ones that we're running there, right? So y hat, an error and loss. So let's forget about these two for now, just focusing on the forward pass. If we do that, you see, basically we're telling, okay, let me visualize the computation graph that PyTorch is using based on this variable. This variable depends on this, and this, right? We know that this is a parameter, this is a parameter, so both of them require gradients, and this is just data. So what's happening here is, if I go from the bottom to the top, y hat is this guy, the green one. It's saying that the operation is adding, because of course it's adding this part with this part. On the left side here, I'm going to have the accumulation of gradients. You can ignore this for now. And this blue one on the left represents B. And here on the other side, we have a multiplication, this multiplication, and this blue represents W. Then the first question could be, okay, we have B and W, but where is X? X is not here, because as I mentioned, X is data. Data does not require gradients, so it does not it's being used to the multiplication, but it's not showing up here. It's not part of the graph. Only the parameters B and W are part of the graph, and everything that depends on them is going to also be here. So you see the y hat is here. If we do error, and then I change here to error, see, now I have also a subtraction because this thing here. And y-train tensor, it's also data, and it's also not showing up as a blue box. If I go still one step further and I go to the loss, then I have this, right? So it's doing the subtraction, is doing the square here, and then the mean in the end. So this green box is going to be the loss. And this is what PyTorch is doing under the hood to keep track of everything that's happening to compute the loss. The moment that you call loss.backward, is going to go to the green one and go backwards and see, oh yeah, I have B here, oh, I have W there. And then it's compute gradients for both of them that you can use to update the parameters. So this is just a way to visualize what's the tree structure of the computation graph that PyTorch is keeping track of. Of course, you don't need to do that in like every time you're running a model. This is just for you to understand what's happening behind the scenes. So basically, I explained what the boxes are, right? Yeah, so I actually jumped the gun a little bit here because this was the loss. I already showed you this. And just for the sake of completion, if I would to turn off the gradient on one of the parameters like this, like B no grad, calling here, and you see, actually now there is only one blue box because the blue box are the parameters that require gradients, right? So this one does not anymore, it's frozen. So you only have one blue box. No gradients, no graph. That's, and you can go crazy, right? If you have, you can have a conditional statement here, like if, I mean, this doesn't make any sense, right? I just made some random if here just to show you. The graph can be something like this, right? So yeah, depending on the condition of the if, it goes like this or it goes like that. Now imagine if you're trying to do that by hand, computing derivatives and stuff. Like, I mean, come on. AutoGrad takes care of everything, and that's awesome. Okay, so we talked a lot about AutoGrad and the computation graph. So let's see if we have more questions in this chunk. Do you think JAX will overtake PyTorch at some stage? Yeah, JAX is another player in the game, and based on the now discontinued Python AutoGrad package that PyTorch was originates from, if I remember correctly. It's even closer to NumPy and standard functional Python. Okay. Yeah, I mean, I can't say much. I have like very little knowledge about JAX. I know that it gets in some traction if you follow like deep learning people on Twitter. There is a lot of people working and very excited about this. Could be that this is something for the future, but I think even if it has some traction and is gonna get bigger in the future, it's still gonna go through the steps that PyTorch had to do itself, right? Like starts in academia, in research, and you can do cool projects with it, but it's still going. If it really takes off, it will take some time until it's also like production ready, as both TensorFlow and PyTorch are at the moment. Okay, cool. Let's go to the next one. So we talked about the gradients and how these AutoGrad can be used to make it easier to compute the gradients. And of course, we need to use the gradients to the main purpose of them is to update the parameters. And this is the role of the optimizer. So the optimizer is going to define a rule that how it's going to use the gradients to update the parameters. What we haven't been doing so far is the stochastic gradient descent with SGD, which is the plain vanilla, the regular kind of optimization. But there are others like Adam, which is fairly popular, very robust, faster, which is like a safe bet for as a choice. But there are others, right? This is Nesterov, accelerated gradient, momentum, AdaGrad, AdaDelta. And this illustration here shows the paths the path that they would take, right? You see the red one is the SGD, it's the slowest one. It goes really slow and doesn't even arrive there. But we're sticking with SGD for now, just because it's simpler, right? But of course, as you progress, you're gonna be able to use the other ones as well. One thing that is important, just because this is called stochastic gradient descent, the name of optimizer, it doesn't mean that you have to forcefully use stochastic gradient descent to update. You don't have to use a single data point every time. You can use all of the data points, or effectively doing batch gradient descent, even if you're using the SGD optimizer. So it's just a name, right? That's what I say here. What's the purpose of the optimizer? You need to tell it, okay, what are the parameters that you want it to keep track of? In this case, we have like B and W, right? So you're going to create an SGD optimizer and tell you, okay, we have B and W here and the learning rate. Because remember, the formula for the update needs the gradients of the parameters and the learning rate. So we can have that. This creates an optimizer. This thing that we have seen here is going to be replaced by a step of the optimizer. The step is going to take all of our parameters and update all of them. But of course, we still need to zero the grants, right? But now, instead of doing one by one, which was fine for 2 parameters, but if you have 1,000, that would be crazy. Now you can zero them in the end. If we run this, now we have, let's see, like half of the stuff is already in PyTorch. We have the same, of course, expected the same results. So yeah, we optimize the optimization process. What's left? We worked on steps 3 and 4 and zeroing. We need to work on these 2. So let's work on step 2 now, which is the loss. We know that for the regression, we need to use mean squared error. And here's the typo again, sorry. But PyTorch, of course, gives you a mean squared loss function. But beware that this is not the function that you're going to use right away, not this one. This is called a higher order function, and it's a function that creates another function for you. Basically, you're telling, okay, PyTorch, we use MSE loss and give me a function that uses the mean, because this could also be sum. And then you will have actually the sum of squared errors instead of the mean. But let's stick with the traditional here, with the mean. If you create this, you see this is a function itself. And then use that function to actually compute the predictions, to use the predictions and the labels or the targets to compute the loss. In this case, if I have these 2 tensors, I'm going to have a loss of 1.6, right? And then we can use this loss function to make the loss function that was created by this higher order function to compute the loss. So this is going to look like this. Always make sure that you always put the predictions first and then the targets later. It doesn't matter for mean squared error because it would work both ways, right? Because it's square, so it doesn't matter. But for other loss functions, the order will matter. So it's always, make sure that you always put them in the right order. Otherwise, you're going to get really weird results. But mean squared error is very forgiven because it's symmetric, right? It doesn't matter. Okay, so we have all the steps in PyTorch. See, the optimizer is here now, right? Only this thing is missing. So this is the model, right? What we have here is just, of course, it's just a simple expansion because our model is quite simple. It's just a linear regression. We can make it nicer now by creating an actual model in PyTorch. So what is a model? A model is a class, and this. So if you are familiar with object-oriented programming, this is going to be easier. But even if it's not your cup of tea, it's okay because we don't have. You only have to know that you need to have 2 methods implemented in a class. This init method, which is the constructor method, this is where you're going to define the parameters, the attributes of your model. And then a forward method that's going to make the predictions. So you basically have to compute what we're doing manually in the training loop. If we do a manual linear regression model, for instance, right, I can create the same B and W that I was doing before. I have to actually wrap them with the parameter class here. So this module class from PyTorch recognizes them as parameters, because just like this, they would not be recognized. But also don't worry much about this, because this would be a very manual construction of a model to show you how it's done. But you're likely using an abstraction of that I will show you shortly. And then the forward method is what is expected, right? It gets the parameters B and W, uses the features here to give you the results. Why is this interesting, right? Because now we have all the logic that's inside the model encapsulated into a single class. If you go back a little bit to this loop, you see that everything else for regression is going to be the same, but this is the model. If I have a much more complex model, all the rest is going to be still the same, right? Which is interesting, because it's going to give us flexibility to use the same training loop just with a different model. Also, another thing is that the moment that you have that, actually you can call the parameters method of the model itself, and it tells you everything. So you don't need to keep track of B and W separately. You can just have all of them as attributes here, and then you're going to get a list of them as a parameter or as a state dictionary. So state dictionaries are very common. You're going to see, okay, B has this value, W has this value, which is more convenient than the parameters because you get the names also, right? Sorry. The state dictionary is going to always give you a snapshot of how the state of the model. That's why it's called the state dictionary. This is going to be very useful if you want to save a model to disk, either for deploying somewhere else or to pause training and starting over again, which is called checkpointing. So you're going to use state dictionaries from the models, but also from optimizers. So optimizer may also have a state dictionary, which is telling, in this case, the learning rate. If you use a more sophisticated optimizer, you're going to have like momentum or Nesterov, other things that you need to know, right? Because if you pause training and you want to go back later on, you need to know what were the conditions under which the model was being trained to continue training. So that's why all the state dictionaries that are relevant to the model train should be kept. We're going to see how to save them in a while. Another important note about the device is that the data and the model need to be on the same device to make it work, right? If you send your data points to the GPU, you also need to send your model to the GPU because they need to be in the same place so the model can access the data points. And the model, just like the tensors, they have the two methods that you can send it to the device. And now you see that in its state dictionary, you're going to have the tensors here with B and W, but now with CUDA because it's a GPU. Finally, the forward pass, which has the forward method that was developed here, right? But there is one catch also. You should not do like this, right? Oops, sorry. You can, in theory, do it like this. It will work. It will give you predictions. But under the hood, what PyTorch does when you make a call to the model as a whole instead of the forward method explicitly, it handles other things behind the scenes. There is something called hooks, which is a way to like monitor or to keep track of what's happening under the hood. You can use hooks to modify gradients, to capture the parameters, to capture the gradients, a lot of things. But all these things are only handled if you call the model like this. So always, avoid calling it with the forward method and make sure to use it as a best practice that all call the whole model itself. So all the extra things that are happening are still happening. In our case, it doesn't matter because we don't have hooks. Our model is simple, so it will not make a difference. But again, it's always good to start doing it in a way that is going to be always correct, right? And then there is one, this is like a pet peeve of mine, probably of many people as well. It's the train method is somewhat deceiving, right? It does not perform a training step. What the train method does is just setting the model to training mode. It's basically just saying, okay, this model is in training mode. The other mode would be evaluation mode, right? So when you want to make predictions for when you're deploying, or you want to evaluate the mode, but the train method only sets the mode. Again, for our simple model, this would be would make a difference. They would be the same if you put this or not. But if your model is more sophisticated and you have like dropout is a different layer. It's a technique that you can use to regularize as a regularization. And it has different behaviors if you are running it in training or evaluation mode. So you need to make sure that you're running in the proper mode, because if you run make predictions using dropout and you forget to put it in evaluation mode, you're going to get weird results. So during the training loop, it's practice to set the model to train. And here you may think that's like wasteful because it's setting at every iteration of the loop. But that's safer because here we still don't have any evaluation. But if you have something else that changes it to evaluation in the middle of the loop, then you know that every time it starts again, it's going to be in the proper mode for training. So I think that's somewhat redundant, but still important. So now you see we have a full loop which sets the training mode, forward pass, loss, gradients, and update. And if you run this, we got the same results. And now the full loop is in PyTorch. We got rid of everything that was NumPy, and we have all the elements in PyTorch already, which is nice, right? Because you see that the logic is the same, and the logic follows the steps of gradient descent. That's why I started with the gradient descent here. But if you think, okay, now this model that we had here, so let me go back a little bit. This seems like an overkill, right? And I agree, because I mean, we only have a linear regression. Why we have to have a full class just for that? This was to illustrate what a model class looked like, but we can go simpler than that. You can use what's called like a nested model. In that case, PyTorch implements what would be a linear model, which would be perfect for a linear regression, like this. It's saying, okay, you have one input and one output, right? This is very simple linear model. In that case, we can modify our custom model and make the PyTorch's linear layer an attribute of our model. This is also somewhat redundant, right? I know that what's happening here is I'm basically taking PyTorch's linear model and wrapping up with my stuff, which is not aggregating anything, right? The constructor is only this, and the forward is just calling linear's forward method itself. This is just, the point of this is just to illustrate that you can have models inside models. I could have, of course, it doesn't make any sense here, but I could have, I don't know, another one, and then maybe something, you could have more things, and then you can make the forward as complex as you want. If you have more complex models, you're going to have many attributes, and these attributes are going to be other layers or other models that you develop yourself. So let's keep it as it was, just for the sake of illustrating a nested model. And you see that if we do that, actually PyTorch keeps track of all this structure, the nested structure, and still it's gonna tell you, oops, if you get the state dictionary or the parameters, is going to go inside and see, okay, yeah, this one is a linear, but the linear itself has a weight and bias, and they're all going to be there. So you can have like a Russian doll with 5 layers or whatever, and still PyTorch is going to keep track of everything. And talking about layers, right? If you have like a neural network like this, where you have like, 3 features, 5 neurons in the hidden layer and 1 output, this could be 2 layers, right? 1, 3 to 5, because you're going from this to that, and the output layer would be 5 to 1. So your mod would be this sequence of layers. Of course, then you have activation functions in the middle, other things, but we're not going to that for now. Just a second. There are many different layers, right? You can have convolution layers, pooling, padding. So these are for computer vision. Normalization layers are used everywhere for sequences, transformer. Linear layers, that one that we are using here. Dropout for regularization. Activation functions, flatten layers. So there are many. Of course, we're not going into details of this. But these are going to be the layers that you're going to use to build more complex models. And finally, if you want to make it really, really simple with the model, we can use what's called a sequential model. If our model is just the input of one, like run-of-the-mill model, like the linear layer, is the input to the next, which is the input to the next, you can just concatenate them in order in a sequential model. In that case, I just have one linear because it's a linear regression, right? And this will be the equivalent of the 2 models that we had seen already. And then if you see this, it's like really simple. You have this. Actually, we can also check the state dictionary of this guy. You see here it's calling 0.weight and 0.bias because it does not have any names, right? But it's still there. So we have models, right? Different ways of constructing models. Now the question is, what we have seen in the training step, right? We had defined an optimizer, a loss function, and a model. If I would change my optimizer from SGD to Adam, or if I were changing my simple model to a little bit more complex model, the loss function doesn't make sense to change here because we're still dealing with the regression, right? But regardless of which combination of these 3 elements I'm using, the training loop is always the same, right? So this is what I would like to highlight here. The training loop, this part here, is always the same. Sets the mode, forward pass, loss, gradients, updates, right? So what I'm doing here is just a method that takes the combination of model, loss function, optimizer, and generates this is a function that builds another function that performs a training step. Then I can simplify a little bit my training loop by create the elements that I need that are descriptive of the problem that I have, right? So that we have a linear regression, mean squared error, SGD. And then I make this. Whoops, oh, sorry, I didn't run this. There you go. This is a function. What this function takes, features and targets or labels. So I can get my X trained tensor and my Y trained tensor, and I run a training step. It's going to give me back a loss. So basically got all this gradient descent complexity and encapsulated into this method here. And every time I create a bunch of stuff that I want, I can create this function that builds me a function that's always going to perform a training step. And if I call this many times, you see the loss that's being shown here is decreasing, right? So basically, I'm being like the loop person here doing this, right? If I do this enough, I'm gonna eventually get a really small loss. Of course, I'm not doing this manually. But what we did here, we separated the training process into what I call model configuration, basically specifying what I need. Right. So let me run this. And then the model training, which is building a training step function And then instead of me doing like 1,000 times the running the cells, I'm doing a loop that every time it takes one training step and gives me back the loss. So if I now this thing is equivalent to what we have been doing so far for training the model, right? So if we do this, you see, we got the same results. You can even plot the losses. You see that they go really fast here and then a little bit slower. I just plotted 200 epochs here, that's okay. So that was a training loop. Now we have an effective training loop, and we can even make a function that builds a training step for us. And before going into the data set, so let me go back to the question, see if we have any other. When you send the data and the model to the GPU, doesn't that get heavy on the GPU when the data is big? Yes, perfect, excellent question. You're not, I mean, this in this case is really a small data set, so it's okay to send everything to the GPU. Ideally, you will not be doing that all at once. What we're going to see in a short while is that when you do the mini batch gradient descent, you just send one bit mini batch at a time to the GPU. So you save its memory, you only send a little bit, like 16 data points or 4 data points, depending on the data point that you have. And then you make a more economical use of the GPU. So yes, it would be heavy if we were sending a lot of data there. But for our example here, it was fine. But we'll get back to it real soon. So actually, this question was a good motivation for the next topic, because if we want to have a mini batch, you have to split the data somehow, right? And we're also not doing that manually. We're using PyTorch tools to actually make the split into mini batches. But to be able to split into mini batches, first we need to create a data set. Because so far we have been using the X-train and Y-train tensors, but these are just tensors, right? Just like NumPy arrays. They don't have any more complex structure. And for that, we use a data set, which is also a class. Like we were doing with the model, a data set needs to implement some of the methods, like a constructor, which takes whatever arguments are needed so you can build or construct your data set. It could be the tensors, it could be the name of the CSV file, or a folder where data is going to be load on demand. So that's why it connects very well with the question. Then you have the get item, which basically makes the data set work like a list. The same way that you use an index to get the 5th or the 10th element of a list in Python, you can do the same with a data set. So it's very convenient to think of a data set as a list. And each element of that list is a tuple where you have features and labels, right? So this, you can think that it's a list where it returns a tuple with the features and labels. And you can load them on demand, or in our case, we're loading everything because it's just a handful of points. And you also have to describe how to give it a way to represent the length of the data set, because when this is going to be sampled for the mini batch, they're going to be randomly drawing samples from it. It needs to know how far it can go, right? So you need to tell it. So we can create a custom data set, which is, again, very redundant, that takes 2 tensors, one for features, one for labels, makes them attributes. The get item returns the ith element of the features and the ith element of the labels as a tuple, and the length is the length of each one of those, right? We're assuming that they have the same size. So if we have tensors here, we can create a custom data set, and you can take the first element of the data set with here. If we want the 5th, it will be just like a list. And you see that the result of this is a tuple as expected. And yet, actually, here goes the answer to the question. We built our training tensor, but it did not send to a device yet, right? So we are not sending anything to a device here. See, these are still CPU tensors. because we don't want to load the whole training data into a GPU tensor right away. We're going to do this at the mini batch moment. So I mentioned that the data set here is redundant, right? Because it's just getting 2 tensors and returning the one element of each. There is a built-in thing for that in PyTorch, which is called the Tensor data set, which does exactly that, but then you just don't need to code the full class for it, right? You can just get this, and again, if you want to get the 5th element, you see this is exactly the same. So now we know how to wrap our tensors or how to construct a data set. The purpose of it, besides of having it more organized, is that now we can use what's called a data loader. A data loader is going to operate on top of a data set, and you're going to tell you how many samples, how many examples, data points you want to use as a mini batch. And then it will take care of everything, right? It's gonna, if you prompt it to get 1 mini batch, it's gonna give you 16 data points in that case. If you get, oh, give me another one, it's gonna give you a different 16, and it keeps track of what has been used already. So you know that next time you're gonna get a different set until you run out of all of them, and then you go back and start again. So that's very convenient, right? Because all this sampling and organizing, keeping track of what's what, it's being handled by the data loader behind the scenes. One thing that's important here, most of the time you want to make it shuffle equals true, because ideally you want to randomize your data, right? You don't know if maybe the data that you're getting from some place is ordered to some extent. You don't want that. You want it to really be random. Just be aware that if in any case you're handling time series data with the time dependence, then maybe shuffle is not for you. That's the only thing that you need to be aware of, that shuffling is fine for data that does not have any underlying structure between different data points, but for time series, just be careful. Of course, we're not doing that here. We're doing the regular shuffle. It also comes with the size, right? Size of the mini batch, that's a tricky question. Most of the time, people like to use powers of 2. There is even a tweet from Ian LeCun that said, yeah, friends, they don't let friends use mini batch sizes larger than 32. This is somewhat old already. You see many places using batch sizes that are larger. But if you have large models, you have to downsize on this mini batch size, otherwise it won't fit into the GPU. But again, there's some nuances to this topic, but for now we can use like 16, 32, 64 for this simple example. It should be fine. A data loader, as I said, you can ask it to give you a mini batch. This is an iterator, right? So every time you can call next, you're going to give you a batch. Oops, I didn't run this. Sorry. You're going to give you 16 features and 16 labels in this case. It's going to give you a tuple of features on one and the other with the labels, with the size that you asked for. So how does this change our training loop, right? So you see, model configuration is the same, right? Because we're not changing the model anymore. We still have the training stamp here, which is fine, but now we have an inner loop. Since we have a training loader here, what we do now, we loop through it, right? And we know that every time it's going to give us back a batch of features and targets. And we get each one of those, and then we send to the device, right? Because at this moment, we're going to say, okay, GPU, take these 16 data points and use them. And not everything. So we are being very economical with this. But other than that, the training step is the same, right? But now instead of using all the 80 data points that we had, we're only using 16 every time. So this will be, for 1,000 epochs, this is going to run 5 times at each epoch. Because now one epoch has 5 updates. If you run this, you see that it will take more time. Because of course, it is now, instead of 1,000 updates, it has 5,000 updates, right? Which is I'm actually showing. Actually, I jumped the gun on the question, right? It's taking longer to train because these are not epochs anymore, but these are updates. And you also may realize that before this was very smooth curve, right? And now it's all jagged because that's the effect of mini batch. If you remember one of the first plots graphs that we had, the path of the gradient descent was very nice, and the path of the mini batch was somewhat wiggly, and the stochastic was really crazy, right? So this is the mini batch one. Okay, yeah, so this is what I mentioned with the mini batch. We can work further on organization of our code here, and we can have a function for the mini batch that takes a device, a loader, and the step function. And this is always going to be the same, right? So you loop over the data loader, you send the data to the device, you compute a step, and then you get the losses for that mini batch, and averages over the full set of data points, because after it run 5 times here, in our example, you'll get the average of this. So see how clean our training loop is now? We had defined model and loss function optimizer, create a train step function because it's always going to be the same. We have a mini batch function now, and if you run this, now I'm only running for 200 epochs, right? Because we have 5 updates per each epoch now, but you're still going to get close to the same results. So this is our training loop now. We have only trained, right? We haven't done any kind of validation yet. So we had a performance split in the beginning as well, but we could use PyTorch's random split if you wanted, because at the beginning the split was very manual, right? I was doing with the indexes, and here actually I can use the full data set to create a tensor. And then, similar to what's being done with scikit-learn, we can use random split and say, okay, give me 80 and 20, and then I have 2 data sets, and then I create 1 data loader for each. And see, there is a difference here that shuffle is not in validation because you don't need to shuffle. It doesn't harm, right? There's no problem, but it's like redundant. You don't need to shuffle the validation set, because it does not have any impact on the update of parameters. So it's just for evaluation. It doesn't matter in which order you evaluate them. And if you're curious about the size here, I just use 20 because I have 20 data points in the validation set. I just made it one batch. But so there is no extra meaning on this, just for convenience. Now that, okay, let me run this. Now that we have validation loaders for both of them, data loaders for both of them, we can actually use the validation loader to actually evaluate, right? So sorry, that was a bit chaotic. What's the difference between the training and the evaluation? First is the mode, as I mentioned before, right? You still have to compute the predictions, and you still have to compute the loss. So you have the validation loss. But you don't need anymore to compute gradients because they don't belong in evaluation. You also don't have to update parameters because they don't belong in validation. So the validation step is going to be shorter than what the training step was. So this builds a validation step based on model and loss function. And also realize that we don't need an optimizer because we're not updating anything. If you put everything together now, I'm calling this data preparation, which is making NumPy arrays into torch tensors. And these are CPU tensors. Make a data set, split, build data loaders for them. Model configuration is still the same. And now the model training, which builds the 2 step functions, has one inner loop with the mini batch inner loop for training. So this is training. And then another one, another one for validation. And you see that this is pretty much the same as this, right? It's the same mini batch function. The only difference is that, again, every time I'm doing evaluation, I'm protecting that part of the code with a no grad. Because it's saying, I know that we are not doing any sort of gradient computation in this function, right? But again, this is like a safety net, because even if I try to do something here, I know that no grad is going to make sure that everything that's running here is not going to affect the computation graph in any way. So you know that you're not messing up with this part. So no gradients in validation. This is very important. If we run both of them, whoops, I'm sorry, I forgot to run. Yeah, I forgot to run this. We got the results, close enough. If you run them, you see this. And you see the validation loss is lower than the training loss. This is somewhat weird, right? You expected that the validation loss is going to be higher than the training loss. But remember the very beginning of this workshop, I told you the validation data is like easier than the training data because the points follow more closely a linear relationship. That's just because this was synthetic data. By accident, it's like that we got a validation set that's easier than the training set. And since it's easier, the model makes a better job fitting into it. And then we have, in the end, validation loss that's lower, but that's circumstantial. Then we can actually put all these parts that we have here in the model training. You can make finally a training loop. And this is going to create the both steps, run all the number of epochs, run the training and the validation, if you provide a validation loader. So basically, I'm all the steps that are necessary for training and evaluating a PyTorch model are being handled by this function. So the job would be to define the appropriate model, the loss function for the task at hand, define an optimizer that I want to use, like SGD or Adam, how many epochs I want to run the loop for, and the training and optionally the validation loaders, because these are the data that I want to use. So this is just organizing everything, right? If you have in the wrapping up of the final code, this is what we do. You build a data set, you make the random split, you build data loaders for your data set, you define a model, a loss function, a learning rate, which is the most important hyperparameter of all, the optimizer, and the number of epochs. So basically work on the data and define the model and the things related to it that you need to train it. And then you're going to use this. This will be like 3 different steps, right? Data preparation, model configuration, and model training. In the end, is just one call to that. So what we did here was, in a way, I mean, of course, it's not like a library or a framework, but it's in a way what other libraries do, like PyTorch Lightning or Catalyst or all the other things. They take a step back and abstract all the details that we have seen so far, because we saw the details of everything, right? We saw how to do all the steps of gradient descent, how to use the optimizer to update parameters, how to use autograd to compute the gradients. But you can do that if you have more complex models, if you want to learn about it, or if you want to explore, you can do it at a very low level, as we did from the beginning. But you see that if you're using different models or optimizer or losses, it's always the same logic, right? So what I did here was, in a way, I got all this boilerplate code for this logic, and in the end, we did step by step, as the name of the workshop, and we built this function that does all the grunt work that we don't have to. We can focus then on organizing our data and defining the proper configuration of the model that we want to train. Did I run this? Yeah, I ran that. So if you run this in the end, you see that you're going to get, again, close to 2 and 1, which we know that are the true values. And if you double check the loss, you have, again, the same loss that we had before. So this was from the very basics of each one of the components to something that's run based on the elements that you configure, and the boilerplate is handled by a separate piece of code. So now I think that's a good time to check questions. How to use momentum and decay. Okay, yeah, this is a bit more advanced. We're not covering it here, but basically it means that you're going to have to use a different optimizer for as you deal with momentum or Nesterov. They also have the decay parameter. Decay parameter is like a regularization parameter that you're going to include there. So this is also configured. It will not change the whole logic of the thing, but it will be necessary if you have more complex models, because this just using a constant learning rate over the whole training sometimes you're not gonna work, right? You may have to use different regimes, like a learning rate scheduler, which is part of the bonus here, but I don't know if we're gonna have enough time to cover it in detail. Yeah, but this would be a more advanced topic. How's the comparison of TensorFlow and PyTorch on mini batch training? What works best for large versus small batch against computational time? I don't know exactly what you mean with the comparison between TensorFlow and PyTorch, in the sense that the logic is still the same, right? If you have, there is a trade-off between the large and small batches, in a sense that if it's too small, you're gonna have too much noise, so it has effects on different components as well. Like if very many models use batch normalization, and in that case, if the batch size is too small, this is going to have a negative impact on it because it's going to fluctuate a lot. So you're going to need larger batch sizes. But if it's too large, then it will take much time. And for instance, if you try to, I was trying to train like one update of the DStillBERT model for natural language processing, and in my GPU, which is like 6 gigs, it cannot take more than 2 samples at a time, which is like really doesn't make much sense. So I have to use the gradient accumulation to overcome that. But then Hugging Face has that under the hood. So these are more demanding topics that I can cover in such a short time. But I think that gives you an idea of the impact of mini batch size on things. But I can't say much about comparison TensorFlow and PyTorch. I don't see how this would be a major difference between them on this. Okay, yeah. So we train models, right? We haven't said anything about pausing the training or deploying them. This is not like a real deployment, but making sure that it's gonna be trained and saved somewhere that can be deployed later. One thing that I mentioned was the state dictionaries, right? For both for both model and optimizer, because our optimizer was simple. It doesn't change over time, but as in the question, if you have used the momentum or decay, you may have statistics that are computed every time you have an update, and these will need to be stored if you want to pause and start later. So this is important to keep track of. Then you may do whatever else you want, like loss and the epoch or whatever. The way of saving a model is fairly straightforward. You just build a dictionary yourself with all the stuff that you want. These are free to choose the keys, right? And then once you have a dictionary, you use torch save, and this will save to disk. Now you have a PTH file. This is just a conventional extension, doesn't mean anything. And this can be either used for resuming training or for prediction or deployment later. If you want to load it back, then you need to know what your checkpoint is. You use Torchload. This is going to bring back the dictionary that you saved, and then you have to get the key that you define for the model state and the one for the optimizer, and then use, like, if you load a brand new untrained model and you use load state dictionary, it will load the weights and all the parameters that were stored for it. Sorry. And then everything else is just a dictionary, right? So you can retrieve it like this. Again, and I want to stress this, if you are checkpointing for resuming training later, set it to model train after loading. Or if you're using a boilerplate code that does this all the time, that's awesome. If you want to make predictions for some deployment or evaluation, then make sure that you use model evaluation after loading it, so you know that it's always in proper mode. Let's see how we are at time. We have some minutes, so I can quickly go over this. So this relates to one of the questions, right? If you in more complex models, you're not using like a single learning rate constant over time. You're gonna want to cycle it or to decay it, in a sense that you may have a learning rate that's like step by step going smaller and smaller. There are many different ways, like step, multi-step, lambda, exponential, cosine annealing. You may have this one that's particularly useful, which is reduce the learning rate on a plateau. If you remember that in the plot with the learning rate, when it was too high, it will get the loss would get stuck at a high level. So it's on plateau, it's stuck for a while. Then you're gonna say it's gonna give you a patient argument. Basically, yeah, if there's 5 epochs without any changes, just try something smaller, and then you go smaller. The reasoning is that after some time, if the learning rate may be too big, too high for the problem, after you advance a little bit, and then you make it smaller so you can explore it in more fine-grained the loss surface. Like, let's put it like this. There are different ways of also doing that, which is a cyclic. Basically, you have a high learning rate, you're like exploring around, and then it goes slow, and then you go fine-grained, and then it goes up again, so you can jump, and so exploration, exploitation trade-off, something like this. The scheduler itself is an argument of the optimizer, because the optimizer is the one that performs the update using a learning rate. So if you want to change the learning rate midway, you need to tell the optimizer. So that's why this is an argument. And the scheduler itself also has a step method, which depends on which kind of scheduler that you're using is going to have a different place, right? So here is, like I said, this is more of a little bit more advanced. I place it here so you can export it further if you're interested. But for instance, just give you an example. I create an optimizer here, and then I create a scheduler, right? So basically, actually, I made a mistake. I said that the scheduler is on a parameter of the optimizer. It's the other way around. You see here, create the optimizer, and then this guy is a parameter, an argument of the scheduler. And then just to illustrate how this would work, you're gonna have to have here, right? After I did the training and after I did the validation, then I have the scheduler here in the end. And then if this one is gonna need to you need to provide the loss, right? Because I mean, how could the scheduler reduce the learning rate on a loss plateau if it was not aware of the loss, right? So you need to tell it. Otherwise, it's just a regular step. So if you do this, we can run the whole thing again. You got similar results, and actually this would be what the learning rate is doing. You see, our learning rate started at 0.1, and then it goes a little bit lower and lower and lower until it's a really, really low, and then it doesn't it doesn't budge anymore. Right? So this was like a scheduler which I used was reduce learning rate on plateau. Basically, as the loss goes down, when it gets somewhat stuck, the scheduler does its thing and makes it lower. We can check the loss here. You see, actually, in this case, it's hard to see that it got stuck at 50 something epochs, right? So yeah, it got stuck here and got lower, but you see, the model had learned what it had to learn already, right? Because it's very simple. So it tried, it waited some epochs, got patience, okay, yeah, not good enough, lower, and then so on and so forth. So this is just an example. Okay, let me see if we have more questions before I go. Thanks, Daniel. Great seminar. Thanks. That's really nice to hear. Would you please give the differences and similarities between PyTorch and PyTorch Lightning? So PyTorch Lightning is, as I mentioned, it's like tries to abstract the boilerplate code, so you don't have to go through the steps, the 5 steps of gradient descent that we were doing, like optimizer step and the backward on the loss. So you don't need to worry much about that. You can just focus on defining the model and the loss and everything else. And in a much more sophisticated way than me, it's gonna be doing what the training loop function that we have did, right? So you see, where is it? So this train loop, right? This function that we built, this thing here, and all these internals, these are going to be much nicer and fancier with PyTorch Lightning because it's built on top of PyTorch to make the development easier for you. So if you don't have any special requirements, in a sense that's something that's really unorthodox, and you want to train like regular models, you can use Lightning to make it much more compact. Instead of having lots of lines of code, you're going to have just a handful. Hugging Face library is also somewhat like this for NLP stuff. You just load just a handful of lines. They even have a trainer class that does a lot of stuff, and you don't have to worry about the nitty-gritty details. Yeah, I think that's the difference. One thing, so let me start wrapping up. That's good to have 2 hours for this because I did this in 90 minutes and it's really, really fast pace. So what I did here, I developed 30 questions, a quiz with 30 questions in 5 different areas covering the topics that we have seen here. And I built a Google form for it. So if you want, the questions were developed specifically to make you think about the points that can be tricky or misunderstood when you're new to PyTorch. So I'm going to ask you somewhat tricky questions, and then hopefully it will trigger you to think, okay, yeah, this is, or if you get it wrong, you're going to understand why. There are explanations for all of them with the correct answers and everything. It's a Google form, but I don't require, I don't collect emails, and it is completely anonymous, so there is no requirements. I don't think you even need to be logged. You can just open the link, and then you're going to see the questions. And then the only thing that it does, it collects the answers, right? So if any of you replies this, is the aggregated statistics are gonna be shown to me. So yeah, 30 people answer question number 2, 23 got it right, but that's it. No personal information. So you see there are many questions here, and then there are 5 different chunks: module 1, 2, 3, 4, 5. So I think that they can be useful to consolidate the knowledge. Yes, okay, so final thoughts. Yeah, I think the idea was to show you all the steps to learn in an incremental way using a very simple example. That was my goal here. Once you have the good handle on this, you can surely go through the official tutorials and hopefully it will be easier for you. If you have any thoughts or questions, you can contact me on LinkedIn or Twitter or on GitHub also. This is my book. Actually, I'm selling it on Limpub. That's 1,200 pages long because it has the fundamentals, which is the part that I showed you here, but there is a lot of stuff, computer vision and NLP as well. And I'm working on, I split it in 3 volumes, and I'm going to have them available on Amazon, hopefully in a month or so. So if you would like to learn more about it, the notebooks are free in the GitHub repo. You have all of them there if you check it, not only for this part, but for all the chapters. I hope you liked it, and I think it's almost close. If you have any more questions, please let me know.
Yeah, thank you very much. This was amazing. We'll give 1 minute for questions, but I think most of them have been asked, if not all. Yeah, I think let's lead a virtual round of applause. Just hear me clapping for everyone. But thank you very much for your time. And yeah, this will be recorded, so it will be available. But otherwise, thank you very much for your time, Daniel. And then we'll end the session there.
Okay, thank you very much for having me here. It was my pleasure. Hope you liked it, and let me know and get in touch if you need anything. I'm here to help.
Thank you very much.
Thanks.
Bye, everyone.
Okay, bye-bye.